Now that we're done talking about particle kinematics, we can go on to particle kinetics. And you can think of the difference between kinematics and kinetics this way. Kinematics is just about relationships between quantities you can observe from a videotape. So those quantities are position, velocity, acceleration. That would also include angular velocity, angular acceleration. Kinetics now, what we're going into is not just about these quantities that describe motion, but they also talk about the causes of motion. So we're still going to talk about all these quantities that we talked about in kinematics, but now we're going to be talking about forces, mass. We're going to be talking about moments, moment of inertia. So that's the change that happens between kinematics and kinetics. If we're talking about particles, then we're not going to be talking about moments and moment of inertia yet. And so the most important equation that we're going to deal with for particle kinetics, and this holds only in an inertial coordinate system, so if your coordinate system is inertial, then you can use Newton's second law, which says force, the net force on the object is equal to the mass of the object times the object's acceleration. So this F I'll write as the sum of external force vectors and remember you have to keep in mind that this is on some chosen object. The mass is the mass of the chosen object, and A is the acceleration of that chosen object. And based on these little summaries, you can see that it's going to be really important in using Newton's second law correctly to identify carefully what your chosen object is. Because if you're not thinking carefully about it and you lump more stuff in than you meant to, what's external and what's an internal force changes, and you end up making mistakes. And that's why in order to use Newton's second law, I'm always going to require that you draw a free body diagram. So every application of Newton's second law needs to have its own free body diagram drawn. We're going to see when we get to rotational kinetics that when you use the rotational version of Newton's second law, I'm going to expect you to have a free body diagram for that too. But for particles, there's no rotational Newton's second law because an object that doesn't have any, that can't have orientation, you can't do calculations involving rotations of that object. Okay, so free body diagrams. I'm always going to abbreviate that FBD. I'm going to, hold you accountable to this. Anytime you use Newton's second law, you need to draw a free body diagram. for every use of Newton's second law and the rotational equation too that we're going to get to in not too long. So here's what you need in your free body diagram. First, you need a closed outline of your chosen object. That means no stick figures, no inner details, and you're not going to draw anything that's not part of your chosen body. So don't draw the ground if the ground isn't part of your isolated system. Okay. And the other thing is you're going to put all forces and couples that are external to the object that are acting on the object. Okay, so draw all external forces and couples on your chosen object. So now there's some rules about how to represent these forces and couples. First, if the direction is known but not the magnitude, then indicate the direction with an arrow and label the arrow with a scalar variable. On the other hand, if you don't know the direction or the magnitude, draw a little coordinate system and label that little coordinate system with a vector variable. Okay, so let me just give little examples of both of these. So A, if you know the direction but don't know the magnitude, you'd indicate that force with the arrow in whatever direction it's acting, and then some scalar variable, capital V in this case, would indicate a speed. And so if you know the direction of a velocity vector, this would be a way to represent its vector. You know it's acting in this direction, and you know its magnitude is equal to the speed. If you don't know anything about the direction or the magnitude, then you have this little coordinate system, and you have two unknown, if it's a 2D problem, you have a full vector of unknown values, and so the variable itself is a vector. But notice that in part A, in that example, what we have here is a scalar unknown. That's one unknown. In a 2D problem, what we have in part B here is we have two unknown components. So for part A, we had a single unknown we had to solve for. For part B, we had two unknowns we had to solve for. And there are two important things that you should remember. First, how do you figure out what forces, and later when we get to rotations and rigid bodies, we'll also be talking about couples. How do you figure out what loads act external to the chosen object? Well, first, there are going to be body forces. The most common one, the one that you'll pretty much always have to deal with, is gravity, weight. But then in some cases, you might be talking about electric or magnetic fields. Okay, so first account for those things. And then the only other thing you have to worry about is imagine going around the outside of the body and just taking inventory of where there's contact made with another object. Those contact points create loads that we'll call tractions. And so everywhere that there's contact, between your chosen object and its surroundings, where there's contact between your chosen object and things outside of your chosen isolated system. Okay, the other important thing you need to remember, besides how to figure out what forces, what loads are acting, is that you must have a free body diagram to use Newton's second law. Okay, otherwise on tests you'll lose points. It's a really bad habit to get into to ever skip doing the free body diagram, because it can help you so much. Essentially what a free body diagram does is it inventories all the things that are going to be added up on, where's Newton's second law? In Newton's second law, it gives you a list of all the things you're going to add up on the left side. Okay, so your free body diagram tells you everything to put on the left. Your kinematic analysis tells you everything that goes into the acceleration on the right. Combine those two, and then you just have algebra to do to solve for whatever unknowns there are. Okay, so let me do a couple examples. Here's one. This was a case I saw on the way to work today on Normandale Boulevard. There was a truck, I don't know, I guess it was broken down, parked on the side. Flatbed truck. So it's resting on the ground, and there was someone pushing the truck, trying to, couldn't see what exactly was going on, but trying to push it out of some kind of puddle or something. Okay. And sitting on the truck was a pig, of course. That's pretty typical around 8 or 9 in the morning around here. And sitting on the pig was some kind of giant bird, maybe an ostrich. I'm sure it was probably just lost. Maybe a crane. And then fighting against this guy pushing, of course, was this helicopter had slung a cable over him. So that was there. Okay. So that was pretty much the scene. There was a few other things going on, clowns and whatnot, but we'll just leave it at this for now. And so let's say we want to do the following things. We want to draw a free body diagram of the truck. And let's say second, we want to do a free body diagram of the pig. Okay. So first, the truck. Well, a free body diagram needs to have an outline with no inner details drawn. So here's the outline of the truck. No inner details drawn, and nothing external to the chosen body is drawn. So I didn't draw the ground, I didn't draw the person, anything like that, the pig, anything. And now we just have to go around the boundary. Well, okay, sorry. The first step we need to do is apply the body forces. We're assuming that we're not worrying about electric fields or magnetic fields or anything. That stuff isn't producing any important forces. But there is going to be weight. And so there's a downward force. That's the mass of the truck times 9.81 meters per second squared. And now we have to just mentally go around the boundary of the chosen body, looking for places where there's contact. Okay, I'll start over here. So we go around, around, around. We get to the wheels, and you could do each one separately if that's important. Since this is just a particle analysis, we don't care about that. So I'm going to just say that there's a force pushing up from the ground. And I'll call that F ground. Since I drew these as arrows, that indicates that I know the direction and I don't know the magnitude. So that's why my variable associated with this force is a scalar. It's not a vector. Okay, so now keep going around. There's a force on this wheel too, but we lumped them all into this one. And then there's a force applied by the man. The man is pushing to the left of the page. So the direction is like this, and I'll call that F man. And here's the first place that things sometimes can get a little confusing. What's going on with the helicopter? Of course, the helicopter pulling on the man affects the motion of this whole system. So should that be in here too? Well, the answer is no. And that's why I tried to give you that sort of specific approach to thinking about it. You don't draw anything that isn't acting directly on the boundary of your chosen object. So the man is pushing directly on the truck, but the helicopter is pulling, or that helicopter's cable is pulling on the man. It's not pulling on the truck. So it does not appear here. And when you're new to this, that might be confusing. Like, how do you not get the wrong answer ignoring this important thing? Well, we'll see that the forces applied by external things on other external things come through in the forces the way we're drawing them. But the forces that we draw are only the forces on the chosen object by external things on the surroundings of the object, on the boundary. And then the last thing we have pushing down is the force applied to the truck by the pig. Okay, so there's a complete free body diagram of the truck. And we'd see, if we went into full analysis of this, that the force applied by the pig is affected by the bird, and the force applied by the man is affected by the helicopter, but that doesn't appear in this free body diagram. That would take a different free body diagram and a different application of Newton's second law. Okay, so now let's go on to the pig. So first, we know we're going to draw the outline. That is a terrible pig. Okay, a little better. Okay, so there's the outline of the pig. What forces are acting? The only body force is gravity, and that's the mass of the pig times 9.81 meters per second squared. Then there's a force pushing up by the truck and a force pushing down by the bird. So that's a complete free body diagram of the pig. Okay, the next thing we want to do is talk about a notation for forces that's going to help us a lot with our bookkeeping. I'm going to call this the subscript notation. And you can use it for any force vectors. You could also use it with couples. The force that is labeled FAB, so this is a force vector, is the force vector applied to body A by body B. Okay, so the first subscript gives you the represents the body that's being acted on, and the second subscript represents the body that's applying the force. For couples, you know, if you named your couple MAB, that would be the couple applied to body A by body B. Again, those couples are not going to come up until we talk about rigid bodies, because you can't talk about rotations for things that have zero size. Okay, so let's do an example. And actually, before I do this new example, let's redo that last example problem. With this subscript notation. Okay, so first we had the truck. There was the weight of the truck. There was a force acting up that was called, I guess I call that F ground. And this whole thing, this is kind of a subtle point about this, is called force vector on the truck by the ground. Okay, so why didn't I write FTG here? The answer is this is a scalar. F ground is a scalar. And you don't use this subscript notation with scalars. But when you combine this scalar with the direction given by the arrow, that represents a force vector. And you can, and once you're thinking about it in terms of a vector, you can use this subscript notation. Okay, so same thing over here. The force applied by the man, so call it F man. That's a scalar. You can't use subscript notation there, but the whole direction and magnitude combined gives you the force vector F on the truck by the man. And one last time here, we have the force produced by the pig. That's a scalar, but the magnitude and the direction together are a force vector called the force on the truck by the pig. Okay, let me do another example. So let's say we have a structure, and actually uh, notice this is different than the structures we were just doing in statics. This thing, because of the roller, if you applied any force to either of these members, this would start to move. And so this is a simple linkage. And if we call this body 1 and this body 2, I'm going to draw free body diagrams of 1 and 2. So a free body diagram of body 1, we have the weight, m1g. We have a force vector produced by that pin. So you could think of that as the force vector on 1 by the pin. And you have a force vector at the top on body 1 by body 2. And now let's look at body 2. Here you have the weight of body 2. And now go around the boundary looking for contact. Since this is a roller, we know the direction of that force. And since we know the direction, the variable associated with it is a scalar. At this pin, we have the force on 2 by 1. And now later when you're talking about this, I don't want to put it on the free body diagram, but we can summarize this vector with magnitude r in the direction shown as the force vector on body 2 by the ground or the rollers, depending on what you're isolating. I suppose I'll call it r for rollers. So notice, don't use the subscript notation for scalars. In order for this to work the way we want it to work, we are only going to name force vectors and couple vectors using this convention. So now we can see what the benefit is of the subscript notation. And that is Newton's third law, N3L. And Newton's third law, you've heard the phrase that it's based on for every action there's an equal and opposite reaction. Well, mathematically, the way we're going to think about it is simpler than trying to make sense out of this phrase. Newton's third law, you can think of its definition as being the force vector on body B by body A is equal to the opposite of the force vector on body A by body B. Okay, so if you switch the subscripts, you switch which force is acting on which, you switch the signs. That brings up one question. How do we use Newton's third law in cases where we have our force vector represented as an arrow and a scalar? So when you have forces with a known direction, Newton's third law says when you do what would be switching the subscripts, that is, switch from talking about the force on A by B to talking about the force on B by A, you'll just keep the same scalar variable and switch the direction of the arrow. Okay, so let's go back to the example we had before with that linkage that I just drew. And I'll use Newton's third law so let me show you what the difficulty is that we have here. The way I've drawn it right now, when I first looked at this example, I have two variables here. Say we know the weights. We have two variables here, two more here, and one more here. So that's a total of 7 variables. And you need to come up with 7 equations to solve for those. But now that we have Newton's third law, we know that this force F12 is equal to negative F force 21 and vice versa. So we can take advantage of that to reduce the number of variables. So we'll go back to the previous example. Free body diagram 1. These are the forces acting. One, what did I call that? Force on 1 by the pin. And the free body diagram of body 2, we had F on 2 by 1, but now from Newton's third law we know that this is equal to negative F12, and so we don't have to introduce two new variables here, and we still have the weight, and we still have this upward force. I'll call it R, but as a force vector, that's the force onto by the ground. Or I think before I labeled it as onto by the rollers. Okay, let's do one more thing now. Let's consider the free body diagram of the Earth. Okay. And we're going to lump in with the Earth the pin on the left side and the roller on the right side. Okay, so what do we see here? Well, first, what body forces are acting? Gravity, we're skipping the gravity applied to the Earth by the sun. So what about the gravity on the Earth by itself? That's an internal force, so we don't have to deal with it. There are two forces acting, and those are the gravitational forces on the Earth by the structures, Those are small, obviously, compared to the mass of the Earth. But now let's think about the forces produced by contact with the structure. Okay, so over on the left side, there's a force vector on the pin by member 1. And we've already labeled a variable, and I should have given this a vector symbol. We've already labeled a variable, a vector variable, f1p. So notice that fp1 is negative f1p. And now we haven't introduced any new variables. And if we go to this side, obviously you can tell how big a structure that was. Go to this side, we have the force on the rollers by body 2. And Newton's third law says that's equal to the force on the negative of the force onto by the rollers. So when we did this one, we didn't have to introduce any new variables, and that was all because of Newton's third law. Okay, I want to do one example that just sort of combines this new kinetic information with some of the more complicated kinematic stuff that we did before, so that you can see how kinematics and kinetics go together. And so this is the idea. Say that you have a Ferris wheel in this coordinate system. This point here is higher, higher gravitational potential energy than this point. We're not, like, this isn't a bird's eye view, this is a view from the side. And let's say we have a camera fixed on this Ferris wheel. And as the Ferris wheel rotates around, this camera rotates around. So it's moving in a circular path, but its orientation isn't changing. And that's happening the whole way around. And let's say that the radius of this Ferris wheel is 2 meters. And the Ferris wheel is moving clockwise with a magnitude of like an angular speed that's equal to 3.5 radians per second, an angular acceleration magnitude of 12 radians per second squared, and it's speeding up. And let's say we are, with this camera, we're observing an object that has a mass of 10 kilograms. And let's say that at the top of the motion, so here, at that instant, the camera observes an acceleration vector for that 10 kilogram object of negative 18 meters per second squared, 30 meters per second squared. And we want to know what's the net force on the 10 kilogram object. So we're going to have to use Newton's second law to relate an acceleration to a force. We're also going to have to use the circular motion equations in order to take this observed acceleration and express it in an inertial reference frame. because the origin of, the camera is accelerating. And that's the equivalent of saying that this acceleration vector that's given is expressed in a coordinate system whose origin is accelerating as it moves around the circle. Okay, so remember that so the acceleration vector of the object relative to the ground is equal to the acceleration vector of the object relative to the camera plus the acceleration vector of the camera relative to the ground. This is what's given. This one we have to calculate using the fact that that the camera is moving in circular motion. So this is equal to alpha cross r plus omega cross r. And then finally, once we have this, we'll add these two together, and that'll give us the acceleration of the 10 kilogram object relative to the ground, which is an inertial reference frame. And at that point, we can use Newton's second law. This is moving clockwise. That means that the angular velocity is in the negative z direction with a magnitude of 3.5 radians per second. So omega is equal to 0, 0, negative 3.5. The angular acceleration, this is circular motion. So we know that it's either, we know that the angular acceleration vector is parallel to the angular velocity vector. So it has to be either in the positive or negative z direction. This is speeding up, which means it's in the same direction as omega. So alpha is equal to 0, 0, negative 12. We were told that we're looking at the instant when the camera is at the top of the motion. So our r vector in this case, since the radius is 2 meters, is 0, 2, 0. And now we can calculate our acceleration of the camera relative to the ground. So we have 0, 0, minus 12 crossed with 0, 2, 0 plus 0, 0, minus 3.5 crossed with the quantity 0, 0, negative 3.5 cross 0, 2, 0. Do that calculation and you get a value of negative 24.50. These units are meters per second squared. And finally, we can use the relative motion equation. So the acceleration of the object relative to the ground is equal to negative 18/30 plus 24, negative 24.5. I'll just leave off at this point. The linear accelerations all have 0 z components, so I'll just leave the z components off. And you get an acceleration of 6 meters per second squared, 5.5 meters per second squared. Now we can go to Newton's second law. a free body diagram. Since we're looking for the net force, we don't have to break this up at all. We can just say that take all the forces on this 10 kilogram object and lump them together into this vector called F net. Newton's second law then says F net is equal to the mass times the acceleration. So 60 newtons, 55 newtons.